haven't had the opportunity to do the reading. That is a pity because the lesson you'll take more in if you have. So I know that many of us are under a lot of strain at the end of the term, lots of things due. Um, the prac report is due tomorrow. So I've seen them coming in. So well done with those who've got them in early. I've also started emphasising that the mid-year exams are coming first week of term 3. I changed all sorts of deadlines and I've got myself in a muddle. Can you people tell me what was the latest? I'd have to check my emails. I think that this is the final, but yes, final. I agree. So if there has, yes, that's right. If something is going on and you need to request an extension, it's very difficult for you to have extensions, but we can talk about it. And the same with a mid-year exam. If you don't get organised and if you're not already revising, even if it's just a little bit, you will find that you run out of time. And if you run out of time for the mid-year, you're going to have even more to revise for the external. People who prepare well for the mid-year, that makes everything flow better for the end of the year. Yes, yes, Alex, that's fine. Um, so we've been talking about electromagnetic radiation and how the properties help us to understand what's going on, and that historically it was thought that little particles hit the eye and the eye was responding to those particles, and that's why we could see that light had a particle nature. Mathematical theory and the knowledge of the speed of electromagnetic radiation helped scientists to believe that light was a wave. And what evidence should we be able to observe if light has a wave nature? Yes, other students have told me that. I have to get learning tech to help me out. I believe that I've got the sound counselling on, it just doesn't seem to be working. So if you need me to repeat, please do ask me to repeat. So I'll just say, what evidence should we see if light, you want me to turn it up? See, I've been fooling around. I've turned it down because the background noise is so bad. So I will turn it up. Has that improved things? Okay. Not for Pete, but it has a bit for Josh. I'll put it up even higher, and that might cause other problems. So I've got it up nearly to maximum. How's that, Pete? All right. Okay. Um, I'll ask that question a third time. What evidence should we see that supports the wave nature of light? What do waves do that particles don't? Actually, they do. Waves, if you think of a water wave hitting a cliff, it does actually bounce off the cliff. So is there something else, some other characteristics that waves have that particles don't? I'll tell you. Interference. Waves can interfere, and superposition means that the energy adds together, all right? And so waves, if you get them in a careful pattern, you can see interference patterns. Particles don't. Particles don't join together and get double the mass. They bounce off each other, which is sort of what you were saying earlier, Josh. Um, so particles remain separate, whereas waves can interfere constructively and destructively. And scientists, when they were able to make slits narrow enough, could observe the interference of light. And that's what you saw in the prac, that you saw evidence that light has a wave nature because you saw interference. Well, there's some more observations. So everyone was confident they knew everything about electromagnetic radiation. It was waves. Well, when they began to look at other evidence and try and model it mathematically, it was found that the only way to match experimental data with theoretical data was to say that light, light energy in particular, but any electromagnetic radiation, had a minimum amount of energy. It actually acted like a little packet of energy, a bit like a particle, and we call them photons. So, and that explained by looking at little packets of energy, we could then do mathematical models that suited what was seen with things like hot body irradiation and things like the photoelectric effect, where electromagnetic radiation hits a metal and the metal emits electrons. And if you collect the electrons, it forms a current and you can measure the number of electrons emitted. And so, with the photoelectric effect, if the incident electromagnetic radiation was a wave, then a wave, the energy should add. And if you had electromagnetic radiation shining on a metal and you waited long enough, the energy should add together and eventually an electron would be emitted. Experimental evidence shows that doesn't happen. Either the light has sufficient energy for electrons to be emitted or they're not emitted. More evidence that light is not just acting as a wave, it's acting as if it's got subunits of a minimum energy. Scientists had to re-evaluate, and they saying, well, there's a particle nature to light. We use light because that's what a lot of analysis is around, but it's true for all electromagnetic radiation. So people fooled around with their formulas. They said, we know the energy of electromagnetic radiation is Planck's constant h times by the frequency. We know that a particle has momentum mass times velocity. We also know that we can describe kinetic energy by mc squared, or so the energy of light is, instead of velocity, we've got the speed of light c. So if we put all of those equations together, we can work out an equation for momentum. So if you had a wave nature doesn't have momentum. It's got to have mass times the velocity. We're not saying that light energy has mass. We're saying it acts as if it does. So we call it relativistic mass. So a particle's momentum is calculated times mass times velocity. We can say momentum of electromagnetic photons is Planck's constant h divided by their wavelength. So that's the theory. As people fooled around, like if you had particles of paint, you would expect particles of paint to form a slit on the screen. Well, people were trying to see what happened with light, and if you put ambient light in, little photons of light could still build up for an interference pattern. So they were looking at physical and experimental evidence, and they were finding evidence that actually if we had tiny little packets of energy, so they've got the intensity of the light really low, so single little spots of energy and a time exposure, in actual fact, you do get an interference pattern built up. So they're actually saying a particle nature and a wave nature coexisting. So you need to just have practice at this very simple calculation, and you need to know the formula. E equals HF. And again, this is on your formula sheet, but if you can learn it off by heart, it's easier. And as I write that formula down and I look at the information given, I'm given a wavelength. So you've just got to know, I'll just go back here. Oh, it's not actually there. V equals F lambda is the formula you need. So, and because we're talking electromagnetic radiation, instead of writing V, we write C equals F lambda. So you're going to have to combine different formulas to get frequency when you're given wavelength. And momentum P is written in terms of wavelength. So you're going to quite often need to swap between frequency and wavelength. So I very briefly mentioned that one of the characteristics that experimenters were very interested in was what is now called the photoelectric effect. So if you look at the number of electrons that are emitted from a metal, what they found is that if there was background ultraviolet light, that far more electrons were emitted. So they started to become interested in, why? What on earth was going on? So when they played around, they found that if you started off with low energy radiation, let's say we started with red, that maybe no electrons would be emitted. But at some point, for a certain metal, electrons would suddenly begin to be emitted. So that was the first interesting thing. The next thing was that once you had electrons being emitted, if you increased the intensity, so intensity is the number of photons per second. So if you increase the intensity of the incident light, then the number of electrons emitted was greater, but the electrons emitted had about the same amount of energy. Now, it wasn't exactly the same. They actually noticed that there were sort of like groups of energy that the electrons had emitted. So it depended whether the electrons, how bonded into the metal surface they were. But often the limits are what is interesting. So the limit was the maximum energy. So what they found is the electron that was the least bound moved off with the most kinetic energy. So I'm just seeing that text chat from Alex. Yes, intensity is the number of photons per second. All right? So a greater intensity is a greater number of photons per second. So they might have thought that if you had more intensity, then the electrons would be emitted with more kinetic energy. But that is not what they found. They found that the maximum kinetic energy was not increased. The number of electrons increased, but their energy didn't. So that supports the idea that the ultraviolet light had little packets of energy that were a fixed amount. So if you had a little fixed amount of energy that hit, and that energy was sufficient, an electron would be emitted. So if you drop down to the red, and the red, of course, is a longer wavelength, less energy, that it didn't matter how many little packets of red energy, if a little packet of red energy was not enough, having 20 not enough made no difference. So again, the photoelectric effect is making scientists realize that electromagnetic radiation is acting with what we call a particle nature. So here we're talking about how the electrons in a metal are bound to the metal. So if an electron is bound with 13.6 electron volts of energy, so that's non-standard use of energy, we've got to calculate how much energy will the incoming radiation require for that electron to be removed from the surface. So that is called the threshold frequency, the lowest energy photon for the least bound electron to be emitted. So just have a quick look. Energy is H times F. Here's Planck's constant. And we've got the charge on a proton. Now, I've got a question for you guys. If you are told the charge is a single positive, what is the size of the charge? I'll go on. It's the same. Yes, this charge on a proton is the same size charge as the charge on an electron. If we have one negative, the charge is 1.6 by 10 to the minus 19 in size. If we have one positive, it's 1.6 by 10 to the minus 19 coulombs in size. Um, so that's just something that sometimes students get tripped up on. It's a bit of knowledge that we assume, but it's not always something that's known. So we've got 13.6 electron volts of binding energy. So the first thing to do is to convert that to joules because we want standard energy. So to change it to joules, we're going to divide by the charge on an electron. And what I'm demonstrating is that you need to write down, even though you're going to put this on your calculator, you need to show you're working, just in case you hit the wrong button on your calculator. And this is very poor setting out. I'm going to do it in a line. Could you also text chat your responses? We'll see if we get the same answers. 13.6. What have I done? I want to multiply it by the charge on an electron. So energy is potential difference times charge. Time. So you would have seen that. 2.17. I got 2.17, which it rounds off to 2.18, or 10 to the minus 18. Now, so once we've got the energy, we can use the formula E equals HF. So we've worked out the energy, the binding energy of the electron. So the energy of the incoming photon has to match that. So the minimum energy for that electron to be released is going to be 2.18. So we can now work out the frequency by dividing the energy required by Planck's constant. So this time, can you type your answer? So several people have, so well done. So I want to look at how you've typed your answer for the threshold frequency. Now you won't, it's not easy to put the little zero down the bottom. That's what we do for the symbol for threshold frequency. And if, like me, you've still got energy showing on your calculator, all you have to do is divide by Planck's constant. Okay, so Pete, you've got a non-standard, well, actually, you have, it is true that seconds to the minus one is what you could say the units were, but we don't use that. We've got respectfully acknowledging somebody. That's it. And it's capital H, little z. And the other thing to notice is the magnitude of your answer is about 10 to the 15 hertz. So you're going to find familiarity with the magnitude of the answer. When you forget to put a negative on your calculator or something like that, it's very, very easy to make what I'd call a silly error. But if you begin to know the magnitude of the answer for the frequencies for the photoelectric effect, it helps you to identify some of those mistakes. So it's really good. Callum, I haven't seen, are you doing okay? Yep, that's good. Now, the next question after doing that calculation, if a different metal is used with a higher binding energy, so the electrons, ionic bond or metallic bonding, it's held much more strongly by in the metallic bonding. So we've got a different metal. What would you expect if you've got incident energy that is really close to the old metal threshold frequency? Exactly, Hunter. You'd need more, the threshold frequency would be higher. You would need more energetic incident um, electromagnetic radiation. So that's good. All right, so how would you show double the intensity if you were doing a little diagram like this one? People want to add it in? That's it. And so you'd have double the photons of energy. And because the energy is dependent on the frequency, we do a little frequency line. That's it. And if we've got monochromatic, so one frequency incident, All right, and so then what would we expect if we doubled the intensity of the incident light? What would you expect for the number of electrons emitted? Yep, double. That's it. That's what I want you to realize. What I've tried to do in this diagram is show the electrons close to the surface had enough energy to be emitted. But as soon as the electrons were a bit deeper down in the surface and needed a bit more energy, then they weren't emitted. So just that idea of the kinetic energy of emission is a maximum for the least bound electrons. And so it gets a little bit boring, but that concept of whether you're talking about maximum or minimum is very important because we simplify things by talking about the limits all the time. All right, so let's see about this one. So we've got a graph of maximum kinetic energy of the photon electrons against the intensity. So have a look. Intensity is on the horizontal and the energy, the maximum energy of emission is on the side. Let's make out it's in joules. And intensity is just a number, it has no units. Oh, well, they call them lumens, but yeah, so it does. So if we've got the same frequency of EM radiation on the metal, but a different metal with a lower threshold frequency. So this is the reverse of what was asked before. Can all of you draw on the graph what you would expect to see with this changed metal? So we've got disagreement. We've got some students saying that the kinetic energy, the maximum kinetic energy of the emitted electron, some are saying it will be higher, or 1, and some have said it will be lower. Can I ask the light blue line person to identify themselves? Okay, Josh, thank you. Josh, can you talk about the thinking that helped you to decide to put the line there? All right, so where has the energy gone? So, Josh, I'm just using you as an example, and this is the sort of thinking everyone's got to do. So, Josh, you've decided that the electron's going to emit it with less kinetic energy. So, do you agree we've got the same energy coming in? Where has that energy gone? You're allowed to reconsider. Yes, excellent. So that's the sort of thinking that helps you to reconsider. Are you happy? Does someone want to add to this conversation? Can I have a tick? Have you stuck in your mind you've got the same energy coming in? So give me a tick. So when I read same frequency, I'm saying therefore same energy. So a tick if that is how you think. All right, so Hunter, how do you think? So when you read same frequency, what comes to your mind? Okay. All right. What do you think? Any comments on Hunter's thinking? So the electron is held with less energy. So when I read lower threshold frequency, the metal with lower threshold frequency, I reinterpret that to say that like Hunter, that the electron is held with less energy. It's easier for the electron to be emitted. Has Hunter convinced you? I'm assuming this is Hunter's line up here. Is that you, Hunter? Yep. Has Hunter convinced you to shift your line and say that the electron, only a little bit of energy was absorbed to break it from the threshold of the metal, therefore the rest of the energy goes off as kinetic energy? So if you've changed your mind, you are welcome to rub out your line and put it above the comparative metal. Now, I'm not sure if these comments relate. I've just read if it's high enough energy. Now, so this might be irrelevant, but the way I'm interpreting it is if the first light incident was sufficient energy and then a metal with a lower threshold frequency, smiley face, yeah, it is from earlier. I thought it must have been. All right, but I'm sure that you agree with me that the energy will definitely be enough. All right. So, how many of you do a bit of chem? Even if it was back in year 10, who remembers a little bit of chemistry? All right. So, we'll just really, the next couple of topics, it's just students have a bit more confidence if they've done chemistry. But basically, we really simplify what's going on in an atom. And instead of drawing complicated movement of probability functions of where a moving electron might appear. So these subshell orbitals are probability functions and saying at an instant of time, the electron might be in this position. And what we find is that the motion depends on the energy of the orbital. So what we do is we simplify it no end and we say, let's just draw it by a circle. And the first energy level closest to the nucleus is called the lowest energy level, which means that the electron is bound tightest. Because what we say is that there is a point away from the nucleus where an electron has zero energy. The attraction to the nucleus and the forces external to the atom are an exact balance. That electron would have zero energy, it would not be moving, which is, never quite possible, but there's some point where that electron is now no longer attached to the atom. So zero energy is here, and that's called ionization. Now, the reason we use the word ionization, do any of you chem students know what an ion is? Not quite, Hunter. Can anyone add to Hunter's? Yes, it's a charged particle. So an atom overall has positive and negative charges and the total charge is zero. An ion has got either one less charge or one more. So if you had an electron that gets taken away from the atom, pulled away by some force, then that atom, instead of having zero charge, will now have a positive charge because the negative charge is over here. That process of turning a neutral atom into an ion is called ionization. It's made a charged particle. So the ionization level is where that electron has left the influence of the atom. And so electrons that are bound inside the atom, for our purposes, have negative energy. It's called binding energy. And if they've left the atom totally, then they will be moving and they will have kinetic energy. And the kinetic energy is positive energy. So if you have a photon coming in and it has 10.4 electron volts of energy, and the photon has 10.4 electron volts of energy, the binding energy for ionization, let's say it's 8. How much kinetic energy in electron volts will the electron move away from the atom? So yes, it will. 2.4 electron volts of kinetic energy. So 8 electron volts was used to overcome the binding energy, and then any energy left over, 2.4, allowed it to move off. Now, because we're saying photons are little packets of energy, then the electron can only absorb the whole packet or none. Now, if the whole packet causes the electron to ionize, well, then there's a continuum of kinetic energies. But inside the atom, these energy levels are discrete. So you could excite an electron. I'm just making up numbers here. If this was 2 electron volts, 6, I'll use whole numbers because it's easy, and 7 electron volts. And this time a different photon comes in, and the photon has, and so if the electron is residing, just listen carefully, if the electron is already at 2 electron volts, and we tend not to write the minus, but so we just understand it's bound by 2 electron volts, it's 2 electron volts away, that means, and if ionization is at 7 electron volts, that means it needs 5 electron volts. So what if a photon comes in of 4 electron volts? A little packet, 4 electron volts. What do you think will happen to the electron? Yes. Why? So look at Pete's comment there. Can anyone say why nothing will happen? I'll ask a different question and then we'll see if we can answer the first one. If a little packet of energy came in, that was 2 electron volts. So again, 2 electron volts is not sufficient to ionize. But for our little example here, would a photon of 2 electron volts incident on an electron bound, would anything happen? I better tell you because time's running away. In actual fact, yes, something would happen because the 2 electron volts exactly matches the gap. See that? Oh, no, it doesn't. Bother. If it was incident, and it's not likely to be, if it was incident on an electron in this shell, okay, of 6 electron volts, So nothing would happen to an electron in the lowest energy level. But if we had an electron in the next energy level out, the 6 electron volt energy level, then the gap is exactly 2 electron volts. That electron could absorb the photon. It'll be insufficient to ionize. In a nanosecond, 10 to the minus 9 of a second, it'll drop back. So the packet of energy, if it matches the difference between the orbitals, can be absorbed. But if it's in between, so the 4 electron volt one would also cause a transition. So because between 2 and 6 is exactly 4 electron volts, the inside of the atom, the electron will be excited to another energy level and then it will drop back. But if I had one of 3, if I had a photon of 3 electron volts, it does not match any of the gaps. The electron would not absorb it. The photon would just bounce off. It will be reflected off with no change in energy. So that idea that the photon has to be exactly right for any internal transitions in the atom. So just going back to the photoelectric effect, and next term, when you come in for your last compulsory workshop, the experiment will be on the photoelectric effect. So we have a couple of photoelectric effect units. So understanding how this works is very important. So first of all, we just think about the least bound electron leaving with the most kinetic energy. And so if you have electrons being emitted from the metal up here, then if they've got enough kinetic energy, they're going to jump from one plate to the other. So if we have a 0 reference potential difference with a +1, +3, then the electron would be attracted across the plate and it would accelerate across. If we've got an electron emitted with kinetic energy and we wanted to stop it, we would put a reverse potential. If we put a negative potential, all right, if we started off at 0, there might be enough kinetic energy to get across. But if we begin to build it up, a negative electron is repelled by the negative potential. If we do -1 electron volt, electrons with very low kinetic energy might be stopped. At some point, we can stop every single electron. So if we build up the potential difference or the stopping voltage, let's say everything is stopped at 3 electron volts, then the most energetic electron would have had 3 electron volts of kinetic energy. So that's what's going on. So here it is. The maximum kinetic energy is the charge on an electron, because it is electrons that are emitted from metals, multiplied by the voltage required to stop the electron. And if we plot the frequency of the incident light against the voltage, then the slope of the line will be the same. So the work function is the energy required for the electron to be emitted. So if we find the threshold frequency where electrons begin to be emitted and we plot the graph and we project the graph back, then this measurement is the energy required to break that binding energy. So I want you to do one last thing before we end the lesson. Can you add a graph line for a metal with a greater work function? So that means it takes more energy for for electrons to be emitted in the photoelectric effect. So if there can be a variation of answers, but there's a couple of things I'll be looking for. Now, I just told you as a fact, I haven't actually really explained why, but the slope of the graph stays the same. The slope, if you calculate the slope by dividing Kmax by frequency, you actually find out the slope is Planck's constant. So that light blue line is good. It is parallel. It's got the same slope. So when you calculate the gradient, you're going to get the number for Planck's constant. Now, that's right, a whole variety of parallel lines to the right because the threshold frequency is higher, which means that the amount of energy required to make the electrons emitted, the work function, it's negative of the work function, so it's going to be further down. So drawing your graph, like you really need to understand the meaning of the slope of the graph and why they're parallel. So I've done that extremely quickly. When you do your weekly work, make sure that they'll have a whole heap of graphs for you to look at. Don't just say, oh yes, say why. I understand why it's parallel. I understand why the threshold frequency is greater. Read it slowly and take it in. So there's some summary information that I think I've mainly covered, and photoelectric effect. We did it. We actually got through the lesson just 5 minutes over.